So we've now seen the beginning of programming. Simple expressions, ways of putting them together into more complex things with means of combination, and the very first version of abstraction, giving names to things. But so far all we've been able to do with these pieces is just behave like we're a simple calculator. We can do arithmetic. Let's add one more piece in, which is the ability to make decisions based on tests. And for that, we have to compare things. We have to decide, am I close enough to square root that I'm done? Am I close enough to something else that I'm done? So we have to be able to compare things. And since so far we've just talked about numbers, what are the comparison operators for integers and for floats? They're the things that you might expect from arithmetic. If I and j are any names of variables, they have values as numbers, then we have ways of testing if something is greater than something else, if something is greater than or equal to something else, less than, or equal. So is 2 less than 3? And if I do a simple example over here, 2 less than 3 returns true. That's good. 2.0 greater than 3.0 returns false. Also good. Is 2 less than or equal to 2 returns true. On the other hand, is 2 less than 2 returns false. Simple comparisons. I also want to be able to tell when something's equal. And you might think, oh, that's easy. Is 2 equal to 2? Wait. We already used equal as an assignment statement. So that won't work. And as a consequence, equality is done with double equal. Is 2 equal to 2? So for example, 2 equal to, oops, try that again, returns true. And then finally, if we want to know is something not equal, we use the exclamation point followed by the equal sign, often referred to or pronounced as bang equal or not equal. That will return true if I is not equal to j. Simple comparisons. They're going to let us build the very first kinds of programs that are going to let us make decisions, because based on whether something is true or false, I'm going to be able to decide which operation I want to do next. You're going to get a chance to explore all of these, but these make sense because they're simple arithmetic things other than that double equal sign, which, as I said, is there because equal is already reserved. Once we have logical expressions, we also need to be able to combine them. I might want to say, is something less than this and greater than something else? And so if I have two expressions that are Booleans, I can also combine them using either and, which is true if both are true, or, which is true if either of them are true, and of course not, which will be the opposite. Not A is true if A is false if A is true. Once I've got those pieces, I can put together more complicated expressions to decide tests. How might we use these? Well, here's a simple little example. This is actually a map of MIT. MIT students are always looking for free food. So imagine there's some food stored away somewhere at MIT, and I want to give instructions to a student to find them. All right, this is a complicated map, but we could use a simpler version of it. I've got my student. He's over here with his backpack ready to find that free food, which is way over here, and I want to think about how would I instruct him to get there? What would the tests be that I might want to use? Well, I might say, if you can go to the right, keep going to the right. On the other hand, if you get to the right and it's blocked, change and go forward. Unless both the right and the front are blocked, in which case go to the left. Unless all of them are blocked, in which case backtrack. Won't be perfect, I could still get stuck, but this will work pretty well to get my way through a maze. What I've just described are 4 simple tests to let me think about how I would instruct somebody to solve a problem, in this case trying to find the free food. Oh yeah, I need one more thing, which is to test when I found the food to know when to stop. Simple tests. With those ideas, I can put together the first kind of actually more reasonable or interesting program called a branching program. And it would say in that case of the maze, move forward unless a test is true. That test might be moving to the right is blocked. If it's not blocked to the right, I'm going to do one thing, keep moving forward. If it is blocked to the right, I'm going to move ahead. And a branching program then simply consists of a test, something that's going to return a Boolean true or false. If the test is true, it's going to have some code that tells me what to do in that case. On the other hand, if the test is false, it's going to have some code to tell me what to do in that case. And in either case, once I'm done with those pieces of code, I can pick up the rest of the computation. You can see why it's called a branching program. It takes one of two branches based on that test. In Python, we don't necessarily have to have the false block. We have to have the true block. If this is true, there should be something I would do. But if it's not always the case that I want to do something even when it's not true, I can skip that. With that in mind, I can start now building a little bit more interesting programs. And so here's a simple example. There's some pieces here we're going to come back to. Don't worry about them. Pieces like input, which is going to give me a way to read something in. But what I want you to see here are the tests. And the first case of a branching program is an if statement. That's a special symbol. It is treated differently, and when the Python evaluator sees this, it says, given that's an if, I'm going to evaluate this expression, which should return a Boolean. It says if the remainder of x divided by 2 is equal to 0. Notice the double equal sign there. If it's equal to 0, if that is true, then I want to execute this set of code. It's going to print out a blank line and then print out the word even. If it's not true, I need to tell it what to do, and I use the special symbol else for that. These are often called if-else expressions. If this is true, do this. Otherwise, do that. And here, again, I've got a block of code. In this case, it's going to print out a blank line and then the word odd. In either case, when I'm done with all of that, I'm going to go down to the rest of the code, which is just going to print out a simple thing that says I'm done with this conditional. You could type this in and run it. I invite you to do that. But what I want you to see here is a couple of things. This if-else structure. And I said in a branch there should be three pieces, and you can see them. There's the test. There's the first block. That's the true block. And there's the false block. Now, how did I know, or rather, how did Python know those are the blocks? Because of this indentation right here. The fact that those lines of code are inset are important because it tells us that's an entire block of code. And when I get done here, I'm going to pick back up the rest of the else. And more importantly, when I get done there, it tells me where the rest of the code picks up. Simple example of a branching program. I've already said this, but I want to recap it. I've got a test. It evaluates to true, when in fact in this case x divided by 2 has a remainder of 0. As I've already said, notice the double equal sign rather than a single equal sign to do the comparison. As I've also said, the indentation is really important. It tells us what pieces are associated together. And notice how that indentation gives us a nice visual structure for seeing where the code is, to see the semantic structure of the code. What's the true block? What's the false block? Now, it turns out that you can have nested conditionals. Inside of a block, I could also have a conditional. And that's perfectly fine. It says if this is true, then I'm going to go in and look at this portion. And if this is also true, I'm going to do that. On the other hand, if this is true, but this is false, I'm going to jump down here and run that piece. Again, I invite you to type this in and try it. But it's going to do something that, based on what the value of x is, prints out whether it's divisible by 2 and 3, by 2 and not 3, or by 3 and not 2, as it runs through that sequence of branches appropriately. And finally, we can have compound Booleans. As I said, I have things that can be combined. This is a Boolean, that's a Boolean, and the combination with the and also gives me a Boolean. So in this case, if x is less than y, and x is also less than z, then the combination is true, and I'm going to print out a particular thing. Again, don't worry about what this actually does. What I want you to see is the structure, including one last piece, which is elif, also shorthand for else if. This says if this test is true, do that. But if this test is false, then see if this is true. If that's true, do that. But if it's false, then skip down. In this case, there's an else, and I'll always do this. I could have multiple elif statements. It's a way of giving me a sequence of tests in order. If this is true, do something. If it's false, but this is true, do something. If that's also false, but this is true, do something, and so on. This just then pulls them together. I've got a basic conditional. If this condition is true, do a sequence of expressions. I can also have an if and an else, or I can have an if, a sequence of elifs, and an else. And again, notice how the indentation tells us which things to do associated with which block of code. That indentation is how we are going to capture other pieces as well, and it doesn't have to just be conditionals. I could have something that has other statements inside of it, such as a print statement here. Again, don't worry what this code does. It's a simple piece of code to execute some simple comparisons on numbers. What I want you to see is how we walk through the branches. And with that, we now have the first kind of code. There's one set of blocks, inside of which I've got another set of blocks. And again, if this is true and that's true, I'll get to that point. But if this is true and this is false, so true here but false here, what happens? Oh, there is no code here, so nothing happens. It simply skips out to the end and jumps past. Again, I invite you to try this to see if it works the way I've described it. What I want you to see is the form of it. One other piece I want to remind you of is the fact that when we do comparisons, we need to use the double equal. Equal sign binds a value to a variable. Here I want to compare two things, and this is a standard place. I make it all the time where you'll get a bug. Don't worry when you do it. Python's going to complain at you saying you're trying to do a binding in a place that you can't. But remember, this is a place where when I'm doing a comparison, I want to use the double equal sign in order to make the comparison of two values and return a Boolean. Okay, what have we added? First simple kind of program. Branching programs allow us to make choices and do different things. But it's still the case that at most each statement gets executed once. I might skip a set of statements if I skip over that branch because I don't get there. But as a consequence of this, these are what we would call linear programs. They run in constant time because I execute each instruction at most once. And the maximum time to run the program is going to depend only on the number of instructions that I have there. Still valuable to make some decisions, but it's not going to give us the power that we want to really build interesting algorithms, and that we're going to get to next time.